And so this is called the ion drag fridge effect. And it's been modeled by two different models to happen at Saturn, and it's also been modeled to happen at Jupiter. So, now of course, models can be wrong. They don't have all the physics that reality has. We do the best we can, but you always have to make assumptions here and there. And so, we think that the models, as best as we can tell, we think that they're correct. They could still be wrong. We have to leave open that interpretation. But as far as we are at now, we think auroral energy is not the solution to the giant planet energy crisis. So to describe a little more of the details of how the ion drag fridge effect works, let's look at these figures. So first, I'm showing 4 temperature profiles from the model. The model itself is called STIM, the Saturn Thermosphere Ionosphere Model. Okay? And the relevant papers are listed here, in particular, Mueller-Vodarg et al. 2012. So you can see temperature versus pressure. Decreasing pressure is similar to increasing altitude. Okay? So you can also think of this as an altitude versus temperature profile. At the bottom of the figure, that's the base of the upper atmosphere, or the base of the thermosphere in ionosphere system. Okay? That's where temperature starts increasing in the thermosphere until it asymptotically reaches some constant, more or less constant value in the upper thermosphere. So we see 4 different colors representing different model parameters and the 4 temperature curves that happen at a latitude of 78 degrees south in Saturn's atmosphere. So 78 degrees is important because this is essentially where Saturn's main auroral oval is, meaning this is where the energy deposition from aurora particle precipitation happens, and the heating that follows from that deposition. Okay? Then you also see vertical black bars labeled as Voyager UVS and as UKIRT, UKIRT. Those are temperature observations with uncertainties. Okay? So basically, the point of this figure is that some of the model simulations are able to reproduce very well the observations. A couple others, maybe the red one and maybe the green one, they lead to temperatures that are too large based on the observations. So we may be hesitant to use the parameters in those model runs. Okay? Then, on the right, I show the meridional and zonal flows that are set up in these model runs. Okay? The contours, the color contours that you see, are neutral temperatures in the thermosphere, or in other words, the upper atmosphere. And then we're plotting versus latitude and pressure. Or again, we could think of it as latitude versus altitude as well, where high altitude is at the top, low altitude is at the bottom. So the red area in the color contours is the warmest area of the atmosphere, and that's where the energy deposition happens. That's where most of the heating happens. Then the black arrows indicate the direction of neutral gas flows, in particular the meridional ones. And so you can see that generally you have high temperatures in the polar region, you have cooler temperatures elsewhere. That's a temperature gradient. Nature doesn't like to maintain that gradient, and so that sets up a flow, a transport of energy. Those flows they start out equatorward, so meridional, polar to equator flows, until eventually you can see that those arrows turn down, meaning that instead of continuing to go equatorward, they're now going down in altitude. And finally, those arrows turn back around and they close the circulation cell back with the high altitudes. So ultimately, this figure represents a transport of some energy from the pole towards lower latitudes until you reach a point where that transport is stopped by the ion drag fridge effect. And then the inward flow of neutrals, due to their slower velocity, causes a replacement of neutrals at that particular altitude to come from lower latitudes, and it ultimately cools the low latitude thermosphere. So the dashed white curve you see here represents the boundary in the model between where you have more cooling and more heating. So in fact, as you keep generating more and more energy deposition and more heating in the poles, at least within these model runs, you end up cooling the low latitudes even further. So you make the problem even worse. Okay, so that's a summary of the ion drag fridge effect, which appears to be an effect at Saturn and also Jupiter. We always have to keep in mind that maybe the models are missing some key physics, but we haven't been able to pinpoint what they might be missing yet, so we have to believe what they tell us for now. Now, I'm going to tell you about some observations that may help to shed some new light on the energy crisis at Jupiter. Okay, so these observations deal with, again, the famous ion H3+. So H3+, remember, is a major ion of all the giant planet ionospheres. It has a plethora of infrared emission lines, strong emission lines in the 3 to 4 micron band. That window is an atmospheric window, meaning we can observe H3+ emissions from the giant planets or anywhere else in the universe, from the ground, in particular ground-based telescopes on mountaintops. So in these observations, we used the infrared telescope facility on Mauna Kea in Hawaii, which is called IRTF. And there's an instrument on IRTF, which is a spectrograph called SPEX, S-P-E-X, okay? So a spectrograph has a slit, and remember, the spectral slit gives you spectral information because it lets in light from the slit and then disperses that light into a spectrum. And then along the slit, you just have spatial information. Okay. So in the diagram here, you can see that the spectral slit is aligned north-south, basically along Jupiter's rotational axis. And in the left, figure A, you can see a narrowband infrared filter of Jupiter emission with 2 different scalings. So to the north and the south, where the background is black, that is scaled to show you the auroral emission. So this is bright auroral emission due to an influx of energetic particles ionizing and heating the polar thermosphere of Jupiter. And then to a different scaling, so that we can see the low latitude H3+, you see the middle band. And in particular, you can see basically that the planet is slightly brighter than the background sky, which is good. That means we're seeing H3+ in this bandpass. And you can also see a little bit of an egg-shaped bright spot that is just beneath the spectral slit in this figure. And that's actually the Great Red Spot. So Jupiter's GRS, Great Red Spot, is a giant storm, a hurricane, essentially, that is 1 to 2 Earth diameters in size. So it's a massive hurricane on Jupiter that has been in existence at least as long as we've been able to observe it. So give or take 400 years at Jupiter. So it's a very long-lasting, massive storm system, and also it's a scary-looking red eye. Since we can see it in this figure 1A, that tells us that it's very bright at these wavelengths. Okay. So this was the first sign that something might be happening at the Great Red Spot. But in order to investigate that more carefully, we have to look at what the spectrum is, actually. Because when you have a filter, you include lots of wavelengths that might be H3+, but they might be due to other things that you're not as interested in, such as methane. Okay? So on the right, we show the spectrum that comes from this same observation. And there are 2 scalings here as well. So first, you have wavelength on the x-axis and latitude on the y-axis. You can see the gray shading identifies, essentially, you can see from north to south, there are about 6 regions of gray shading that go from pole to pole, and the bright regions near each pole are the auroral H3+ emissions. And then they sort of tail off and get weaker and weaker as you go to lower and lower latitude. These are 6 H3+ spectral lines. Then we have the colored scaling, which shows you essentially what is happening at the low latitudes, and in particular what is happening at the low latitudes by the Great Red Spot. So what you can see in these contours is that even though the low latitude emission is not bright in general, it gets significantly more bright when these H3 plus lines are directly above the Great Red Spot. So, in other words, the Great Red Spot is excessively bright in H3 plus emission. Okay. Now, remember that H3 plus emission, when carefully analyzed, tells us something about the temperature and the density of the emitting column of gas. Okay? So we can use these observations then to estimate what is the temperature above the Great Red Spot, what is the density of H3 plus above the Great Red Spot. To do that, we need to fit a theoretical spectrum to the observed spectrum. So here I show a model fit to the observed H3 plus spectrum above the Great Red Spot. So the data is shown as black symbols with error bars. And then there's the H3 plus model fit is a solid red line. And we also indicate some other aspects of H3 plus emission that would occur in this bandpass. But we don't use those in the model fit because these regions, specifically around 3.42 microns, would be impacted by other emissions that we're not interested in, such as contamination from the Earth's atmosphere and other emissions from different constituents in Jupiter's atmosphere. Okay? So we're only interested in the region of the spectrum near where the solid red lines are. And if you look in that region of the spectrum, you can see that the model fits very well to the observations. So we can believe that whatever the model parameters are in terms of temperature and density that we use to generate the model spectrum, those are essentially representative of the parameters of the upper atmosphere that we're observing here. So that model fit between the observed spectrum and the theoretical spectrum gives us then a derived temperature and a derived column density of H3 plus. We can do that same thing. We can derive the temperature and column density for each different latitude along that observation where we saw the bright Great Red Spot emission. And we can also do it at different longitudes where the spectral slit was not above the Great Red Spot. Okay, so that's illustrated here. The white shading shows the region of the spectra that we're using to derive temperatures for the spectrum that we call the Great Red Spot spectrum, so the GRS spectra. And the yellow regions are the regions where the spectral slit is relative to the Great Red Spot when we're deriving spectra that we call the non-GRS spectra. Okay? Those show up on the right in terms of derived column average temperatures versus latitude. So just to reiterate, the red symbols in this figure represent temperatures that come from spectra derived when this Great Red Spot was directly beneath the spectral slit, and the blue temperatures come from spectra when the slit was not above the Great Red Spot. Okay, so now knowing that, we can look at what the profile of temperature is with latitude. You can see that there's some variability here, meaning that it's not a constant temperature with latitude, but there's also some values that have relatively high uncertainty, so it's not a surprise. You see that in general, temperatures are larger at higher altitudes, which would be consistent with a heat source that starts in the polar regions and is redistributed globally. But in general, the low latitude temperature of, say, 600 to 800 Kelvin is still much higher than any model can account for. Now, the main point I want to draw your attention to in this figure is the gray shaded region. And that gray shading indicates the latitudes where the Great Red Spot is at Jupiter, okay? So, in particular, there's one red data point that is above 1600 Kelvin. And that similar data point at the same latitude in blue is more than 600 Kelvin cooler, all right? So this figure gives very strong evidence that the temperature above Jupiter's Great Red Spot is much higher than anywhere else on the planet.